This video is part of a series that describes how to implement a simple microcontroller core in System Verilog. In this video, I will talk about how the core interfaces with I/O peripheral devices. Let's begin by describing the two instructions that are used to interface with the I/O peripheral devices. That would be the in instruction and the out instruction. All interfacing between the core and peripheral devices is done by reading from or writing to the so-called I/O registers. There's a set of up to 256 of these I/O registers, so 8 bits is adequate to address any one of these registers. In the two instructions, the opcode byte is followed by an 8-bit number which gives the I/O register that's either being read from in the case of the in instruction or written to in the case of the out instruction. With the in instruction, a byte is moved from the specified I/O register into the A register, and with the out instruction we copy a byte from the A register to the register that's specified in the instruction. Here's a diagram that shows the module structure of our implementation. We have the core module. We have a couple of modules that are concerned with the UART serial communication device, and we have a module called output control that drives the 7-segment LEDs. We're not going to worry about this in this video. Instead, we're going to focus on the interface between the core and the I/O peripheral devices. In our implementation, we're just going to have one device. That is the UART serial communication. Actually, you can think of it as two devices because the transmit module and the receive module are really quite separate. But in any case, we will be using a single register for both the input and the output. We'll use register 0. So to write a character, we'll use an out command with register 0 to send a byte from the A register to the serial communication. And to read, we'll use an in instruction, and that will transfer a byte from the UART into the A register. In many computer systems, we can also check the status of the UART to see whether it is ready to send the next character or to see whether a character has been typed. We're not going to do that in our implementation. Instead, we will have the UART modules force the core to wait. So for example, when we do an in instruction to read a byte, the UART receive module will ask the core to wait until a character has been typed. And likewise, when we use the out instruction to send a byte to the serial communication channel, the UART will suspend the core's execution until that character has been fully sent, and the UART is able to receive another character to be transmitted. Okay, now let's look at these signals here in greater detail. For the output, we have these 4 signals, and for the input, we have these 4 signals. So when an out instruction is executed, these signals will be valid and interface and perform the data transfer to one of the output registers. So in order to do an out instruction, the core will raise this out write enable signal for one cycle, and at the same time it will output a value on the register number and the register data, the register number that we want to be sending data to and the data that is to be written to that register. The I/O peripheral can then raise the output wait signal, and that will suspend the core's execution, and the core will be suspended until the output is available. For the in instruction, we have these signals. When the core wants to read from a register, it will supply the register number and raise the in read command line, and then at some future time the device will provide the data and raise the in ready line. Now let's take a look at a timing diagram that shows what happens when an out instruction is executed. The core will raise the out write enable signal for 1 clock cycle, and during that clock cycle it will also provide the number of the register that we're writing into, as well as the 8 bits of data that we're writing into that register. If the I/O peripheral requires the core to wait, then it will need to raise the out wait signal on the next clock cycle and keep it high for as long as is necessary. In the case of serial communication, the time required to transmit a character is really huge. So for sending a character, there may be a huge number of cycles that are waited, where we wait here. Now let's see what the finite state machine is doing. The fetch cycle occurs first, and that's where the core is sort of figuring out what to do. And then there is an execute cycle during which the core will raise the lines appropriately, and then it will go into the execute to state, and it will remain there until at some point the out wait signal is low, at which time it will go into the fetch state for the next instruction. Now, in the situation where the core doesn't require any waiting, it will never raise the out wait line. So in that case, the instruction will take just 3 cycles and will stay in the execute to cycle for only 1 cycle. Here's a timing diagram that shows what happens when an in instruction is executed. The core will raise this read command line and will keep it high until the peripheral device provides some data. At the same time, it will provide the register number that we're trying to read from, and this will also stay valid through this period. The device itself will keep the ready line low until it has the data to give back to the core. So when the data is valid, it will also raise the ready line for 1 cycle. Now let's see what this looks like with the finite state machine. The fetch cycle is concerned with reading the byte following the opcode, and so we know what register to use. And then on the execute state, the read command and the register numbers are provided, and those will continue to be provided until this instruction is complete. And then we move into the execute to state, where the core will just basically be checking the ready line, and at some point the ready line will go high and the data will be valid, and at that point the core will move into the fetch state for the next instruction, and at the same time it will clock this data into the A register. So if there is no wait required, then this is what it looks like. The peripheral device will raise the ready line on the cycle after the read command is issued, and so there will be no waiting, and we will have just 1 instance of the execute state. So we'll stay in the execute state for only 1 cycle, and the entire instruction will take only 3 cycles. Now let's look at the Verilog code for the out instruction. The first thing we need to do is fetch the byte after the opcode, which is the register number. We'll need that in the second state of the instruction. So the first state of this instruction doesn't do anything really unusual except move into the execute state. And then when we're in the execute state, we will be sending the signals to the output device. Now we need to increment the program counter twice because we have 2 bytes for this instruction, but we don't need to keep incrementing it during all of these states here. So whenever we are going into the execute to state, we will not be incrementing the program counter. Okay, here we are in the fetch state, and let's scroll down to the code for the out instruction, and we see that we use the defaults except that we go into the execute state next. So if we then scroll down to the execute state here and the out instruction here, we see that we are going to proceed from this into the execute state 2, and we will not be updating the program counter. And here we're sending the signals to the output device. We're sending the register number, and that is the 8-bit number that is coming out of the memory, and we are raising the write enable line, and we are providing the data to be written to the output register, and that is just the current value of the A register, which is always available. Now if we look at what happens in the exec2 state, we're basically just watching for this low signal, And when it's high, we stay in the execute to state, but when it's low, we move into the fetch state. So if we scroll down to the execute to state here, and then we find the code for the out instruction, we see exactly that. First of all, we look at the wait line, and if it's high, then we remain in this state, and also we don't increment the program counter. Otherwise, we proceed into the fetch state as normal and finish the instruction. Now let's take a look at the Verilog code for the in instruction, which is similar to the out instruction. It's a 2-byte instruction, so we need to use the first cycle of the instruction to read the byte that follows the opcode byte. That will be the register number, and we'll need it in the next state, next cycle, to supply to the I/O device. So we won't do anything special in the fetch state except go into the execute state. And then in this cycle, the output from the memory will be sent to the I/O device as the register number, and we will also be raising the read command line. And then we'll go into the execute to state. In the execute to state, we will need to continue to supply the register number, so we need to save it. So in the execute state, we will be clocking it into the MSB register, and we'll do that on this rising edge here. And then in the execute to state, we can supply it to as the register number. And we also need to be watching for the ready line to go high, and when the device raises the ready line, then the data will be valid, and we can clock it into the A register. At that point, we will also see that the ready line is high, so we are done with this instruction, and we can go to the fetch state. So let's look at the code for the fetch cycle first. Here it is, and you can see it doesn't do anything too unusual. The defaults are all good, which will continue to read from the program flow and get the next byte. And we go into the execute state, and then if we scroll down here to the execute state, and then we go down to the code for the in instruction, we see that it's doing what we expect. It will be going into the execute to state next, and we don't increment the program counter. And we will also be updating the MSB register. So at this point, the byte that is the register address or the register number is coming out of the memory. So on the next rising edge, we will write it into the MSB register. So we raise the write enable line here. And we will also be sending to the I/O device the register number, which just came out of memory, and we will raise the read command line. Now if we scroll down here to the execute to state, and the code for the in instruction is right here, and we can see that we continue to send to the I/O device the register number. It's now saved in the MSB register, and we also keep the read command line high. Here's where we check the ready line from the I/O device, and if it's not ready, we'll just stay in the execute to state, and we will not be incrementing the program counter. But if when the ready line goes high, we will go into the fetch state, which is the default for the value of next state, and we will be writing the value that we are receiving from the I/O device here into the A register. So we supply it as the data in to the register unit, and we also send the address of the A register, which is just 0, to the register unit, and we raise the write enable line to write one of the 8-bit registers, namely the A register. So that's it for the in instruction, and that's it for both the in and the out instructions. And that concludes this video, and I hope to see you in the next video. Thanks for watching.